As you drift into sleep, millions of kilometers away in Martian orbit, a robotic eye is turned towards the deep starfield. It executes a pre-programmed command, recording the Martian night sky during a specific window. This window was meticulously calculated to coincide with the closest approach of a distant visitor. No one anticipated that this routine observation would capture imagery potentially rewriting astronomical history. An interstellar object named 3I Atlas streaked across the Martian sky at a staggering 60 kilometers per second. This footage was first discovered by an amateur astronomer within publicly available raw data. What followed was a series of astounding anomalies that have left the astronomical community both electrified and perplexed. From inexplicable chemical signatures to the unusual silence from official agencies, a scientific storm is brewing in the silent vacuum of space. We are about to embark on an exploratory journey to examine all the evidence and conjectures. We face a fundamental question: are we witnessing a peculiar comet from another star system? Or are we, for the first time, encountering something far beyond our current understanding? Stephen Burns sat at his computer, as he did on many evenings, processing publicly available data from NASA's websites. This data, transmitted back by the Perseverance rover, is free for anyone to download and analyze. He wasn't searching for anything groundbreaking, merely practicing his image processing skills. He downloaded a sequence of photos of the Martian night sky taken consecutively during a specific 9-minute window. In astrophotography, a common technique called image stacking combines multiple short exposure shots. This method enhances faint signals, revealing details and motions invisible in a single frame. When Burns processed this batch into an animation, he immediately noticed something unusual. The rotation of Mars caused the background stars to drift slowly across the frame, as expected. Yet, one point of light cut across this moving starfield at a different angle and a much higher speed. Its trajectory didn't match any background star or asteroid, it was traversing space near Mars at high velocity. Burns calculated the object's speed, and the result was staggering: 60 kilometers per second. This velocity far exceeds that of most objects within our solar system. For comparison, Earth orbits the Sun at about 30 kilometers per second. Humanity's fastest spacecraft, the Parker Solar Probe, reaches 192 kilometers per second at its closest approach to the Sun. But 3I Atlas wasn't relying on the Sun's extreme proximity, it maintained this blistering pace in the outer solar system. Burns posted his animation online, sending ripples through the amateur astronomy community. Other analysts with image processing skills began downloading the same raw data, applying their own algorithms. It was then that an analyst named Noctave made a claim that heated up the discussion. He stated that in the October 3 data, he saw not one, but multiple such fast-moving objects. Another user, Alexander Ferrum, pointed out another eerie phenomenon: a brief green flash at the 3-second mark in the animation. This flash, highlighted in green, wasn't a single-pixel cosmic ray hit on the camera sensor. It was a diffuse, localized glow, a brief green luminescence in the dark void of space. Green light in space has specific causes. On Earth, we associate it with auroras, burning copper, or even some bioluminescence. In space, green emission typically comes from excited oxygen atoms or a molecule called dicarbon. When comets approach the Sun, solar radiation excites dicarbon in their coma, causing it to glow green. But here's the problem: spectroscopic analysis of 3I Atlas showed virtually no dicarbon in its coma. Astronomers call this characteristic carbon chain depleted, meaning it theoretically shouldn't glow green. Yet, photographs from ground-based telescopes in early September clearly showed a green hue developing around the object. This fleeting green flash in the Mars imagery, if proven real, adds another layer to this mystery. Claims about multiple objects began to surface. When analysts attempted to stabilize the starfield in Burns's animation, accounting for Mars's rotation and the motion of the primary object, they claimed to see at least one or two additional points of light moving at different velocities. These points could be artifacts from the stacking algorithm, or background asteroids that happen to be in the frame. But they could also be fragments breaking off from 3I Atlas, or even smaller companion objects traveling alongside it. This is a question nobody can answer yet, because NASA hasn't released the crucial data. This flyby was no accident. NASA and the European Space Agency had orchestrated and coordinated it carefully. Multiple probes in Martian orbit aimed their high-precision cameras at 3I Atlas's predicted path. This included the high-resolution imaging science experiment, HiRISE, camera on the Mars Reconnaissance Orbiter, the Mars Express, and the Color and Stereo Surface Imaging System, CASIS, on the ExoMars Trace Gas Orbiter. These weren't casual snapshots but pre-planned scientific observations designed to gather the highest resolution data ever of an active interstellar object. The HiRISE camera can resolve features as small as 30 centimeters when imaging the Martian surface. When pointed at 3I Atlas, 29 million kilometers away, its resolution would still be about 30 kilometers per pixel. This means if 3I Atlas has a nucleus 5 kilometers in diameter, it would appear as a bright cluster of pixels in HiRISE images. More importantly, HiRISE could distinguish between a single, compact nucleus and a fragmented or multi-component structure. If there are multiple fragments, if there is a companion object, if there is anything unusual about its structure, HiRISE would see it. So, where are the images? NASA's official statement has been minimal, stating only that the Mars orbiter successfully conducted their observations, data is being processed, and analysis continues. In the world of space imaging, 24 hours is plenty of time to at least preview some raw data. We are now well past 48 hours. Some observers have noted that administrative issues within the US government might be affecting the release of scientific data. But ESA operates independently and should be free from such constraints. Yet, ESA's images haven't appeared either. This synchronized silence feels deliberate. When official channels go quiet, amateur observers start seeking answers themselves. What we know for certain is that the Perseverance rover did capture something. Multiple analysts examining the same public data have reported anomalies. The object, or objects, moved at velocities consistent with 3I Atlas, and that inexplicable green flash is there. What we don't know is whether those apparent multiple objects are real, whether they are separate from the main comet. And what NASA and ESA saw with their far more powerful instruments. The October 3 flyby represented the closest any spacecraft has ever come to an active interstellar object. It was our chance to understand what 3I Atlas really is, to see its structure up close. To determine if it's behaving like a normal comet or like something else entirely. As we wait for answers, the object itself continues its journey. Right now, it is approaching the Sun, moving deeper into the inner solar system, where Earth-based telescopes will lose sight of it against the solar glare. By late October, it will pass behind the Sun, completely hidden from our view. When it re-emerges in November or December, it will either confirm every natural explanation, or it will have done something that comets simply don't do. Rewind to August 15, 1977. Ohio State University's Big Ear radio telescope was conducting a routine sky survey. It automatically scanned narrow bands of radio frequencies, printing intensity readings on continuous paper. 3 days later, astronomer Jerry Emmon was reviewing these printouts when he noticed something that made him grab a red pen. A signal had appeared, strong, narrowband, lasting exactly 72 seconds. Its intensity was far above the background noise. Emmon circled the alphanumeric sequence and wrote the famous word in the margin, "Wow." The signal came from the direction of Sagittarius, near the globular cluster M55, at a frequency of 1420 MHz. This frequency sits within a protected radio astronomy band where no human transmissions are allowed. The signal's bandwidth was less than 10 kHz, exactly what you'd expect from an artificial transmitter, not a natural astronomical source. The Big Ear never detected it again. For nearly 50 years, the WOW signal has remained one of astronomy's deepest mysteries. Until Avi Loeb decided to calculate where 3I Atlas was in 1977. Based on the object's current trajectory and velocity, Loeb traced its path backward through space. In August 1977, 3I Atlas would have been approximately 600 astronomical units from Earth. That's 600 times the Earth-Sun distance, far out in the solar system's outskirts but not yet in true interstellar space. Loeb calculated 3I Atlas's position on August 15, 1977, right ascension 19 hours 21 minutes, declination -19 degrees. The WOW signal's origin was at right ascension 19 hours 25 minutes, declination -27 degrees. A separation of 4 degrees in RA and 8 degrees in December. In astronomical terms, that's remarkably close. The chance of two random sky directions aligning within about 9 degrees of each other is roughly 0.6%. But alignment alone doesn't prove causation. Loeb went further. If 3I Atlas transmitted the WOW signal, how powerful would the transmitter need to be? At a distance of 600 Australian dollars, generating the received intensity would require a transmitter outputting between 0.5 and 2 gigawatts. That's the output range of a typical nuclear power reactor on Earth, not impossible, nor particularly advanced. For a civilization capable of interstellar travel. The WOW signal also showed a slight frequency shift. It was detected at 1420.4556 MHz, about 10 kHz higher than the neutral hydrogen line. This represents a blue shift, meaning the source was moving toward Earth. 3I Atlas is moving toward the Sun at approximately 60 km per second, accounting for Earth's motion and geometry in August 1977. The relative velocity would produce a blue shift. Loeb's calculated expected shift is close to what was observed, though not a perfect match. Differences could be explained by uncertainties in position/velocity vectors, or if the signal was transmitted directionally rather than omnidirectionally. From a strategic standpoint, if you're an intelligence wanting to announce your presence, broadcasting near the hydrogen line makes sense. Hydrogen is the universe's most abundant element. The 21 cm hydrogen line is so fundamental to radio astronomy that any civilization with radio technology would monitor it. It's the galactic calling card frequency. The WOW signal lasted 72 seconds due to the Big Ears operation. It used 2 feed horns listening to adjacent sky regions. As Earth's rotation swept them across the target, each horn had a 36-second window. The signal appeared sequentially in both. This means the source was transmitting continuously, or at least for the duration Big Ear could observe it, not a brief pulse, but a sustained broadcast. If 3I Atlas was responsible, immediate questions arise. Was it a beacon announcing presence? A navigation pulse marking position for another spacecraft? An attempt at communication encoding information we lacked the sophistication to decode? Or was it entirely unrelated, a cosmic coincidence where an interstellar comet happened to align with an unidentified natural radio source? The problem is, we have no radio telescope data on 3I Atlas, not from 1977, obviously, but not from now either. No observatory has reported pointing radio dishes at it. The focus has been on optical observations, spectroscopy, imaging. The questions have been about composition and structure, not about whether it's transmitting. Loeb argues this needs to change immediately. The object is approaching perihelion, getting closer to the Sun. Meaning higher temperatures, more activity, more available energy. If there's any kind of technological system involved, if it transmitted once at 600 Australian dollars. If it's designed to communicate at specific journey points, now would be the time. Radio telescopes like the Very Large Array, Arecibo's successors, and vast arrays in China and Australia could monitor 3I Atlas across multiple frequencies, not just the hydrogen line, looking for any narrowband signals, modulation patterns, or repetitive structures that natural sources don't produce. If there's nothing, fine, it costs a few telescope hours to rule out the hypothesis. But if there's something, if 3I Atlas is emitting radio signals, even faint or intermittent ones, that changes everything about how we interpret this object. Because a comet doesn't broadcast. A chunk of ice and rock, even from another star system, doesn't generate structured radio signals at specific frequencies. Natural astronomical sources produce radio emissions, but they're broadband, chaotic, lacking the structure that indicates intention. The WOW signal had structure. It had a narrow bandwidth. It appeared at a meaningful frequency. And if Avi Loeb is right about the alignment, if the 0.6% coincidence is actually causation, then somewhere in the outer solar system, 48 years ago, something transmitted a signal powerful enough for us to notice. That something is now racing past Mars, hidden behind the Sun from our perspective, doing things that comets aren't supposed to do. The question isn't whether we should be listening. The question is why we aren't already. As comets approach the Sun, they begin shedding material from their surfaces. Ice sublimates directly from solid to gas, dust particles lift off, trapped volatiles escape. Occasionally, if the comet gets hot enough, trace metals vaporize from dust grains embedded in the ice. Nickel and iron appear together in these outgassing plumes. Always together. Because they form together in stellar processes, exist together in meteoritic material, and sublime at similar temperatures. The ratio varies slightly from comet to comet but follows a predictable pattern. For every atom of nickel detected, you expect about 10 atoms of iron. The previous interstellar comet, 2I/Borisov, followed this rule perfectly. Solar system comets follow it. Every icy body we've observed showing metal emission follows it. Except 3I Atlas. The European Very Large Telescope in Chile has been observing it with its UV and visual Echelle spectrograph. An instrument designed to split light into its component wavelengths with extraordinary precision. Between August and September, observers captured spectroscopic data across 6 time periods. As the comet moved from $3.14 down to $2.14 from the Sun. In every observation window, nickel emission lines appeared, bright, clear, unmistakable. Iron appeared only when the comet got closer than $2.64. Before that threshold, nickel without iron. After, nickel with some iron, but in ratios completely unlike anything seen in other comets. The nickel-to-iron ratio measured orders of magnitude higher than solar abundance ratios. Higher than typical cometary ratios, higher than natural geological processes would produce. The production rate made it stranger. 3I Atlas was releasing nickel gas at 5 grams per second when first observed. As it got closer and warmed, that rate increased dramatically. 5 grams per second sounds small. Until you consider, that's 430 kilograms per day, over 3 tons of nickel per week. From an object supposedly made primarily of water ice and rock. The surface temperature at $2.80, where much emission was observed, is far too low to vaporize silicate minerals or metallic nickel/iron grains. The comet would need to be at least twice as close to the Sun for normal refractory material sublimation. Something else is happening. The research team proposed possibilities. Perhaps nickel exists in a volatile form like nickel tetracarbonyl, which breaks down under UV light, releasing free nickel atoms. But forming nickel tetracarbonyl requires specific chemistry, conditions, and pathways uncommon in natural processes. On Earth, we produce it industrially via the Mond process to purify nickel from ore. The chemical signature of 3I Atlas mimics this industrial refining process output. Another possibility, nickel embedded in organic compounds or as nanoscale particles responding differently to solar heating. Perhaps photon-stimulated desorption preferentially releases nickel. These are plausible natural mechanisms, complex, requiring specific conditions, but possible. Except natural mechanisms leave evidence, require precursor materials, depend on formation history and radiation environment. 3I Atlas likely formed in the Milky Way's thick disk, an older, metal-poor region. Models suggest it spent 4 to 7 billion years traveling through interstellar space before entering our solar system. During that journey, exposed to cosmic rays, background radiation, interstellar dust/gas collisions. Could that exposure create exotic surface chemistry explaining the nickel emission? Could it have accumulated journey material that now, sun-heated, releases metals in unusual ratios? You'd expect chemical differences in comets from different stars. Different protoplanetary disks have different compositions. Element mixes, volatile/refractory ratios, organic molecule structures, all vary based on formation location/time. But the laws of physics don't change. Nickel and iron still form together in supernovae. Condense together in protoplanetary disks, sublime at similar temperatures. Getting them to separate, releasing in dramatically different ratios, requires overcoming fundamental chemical relationships. Unless the nickel isn't sublimating from ice/rock. Unless it's released via chemistry we don't typically associate with comets. Loeb, predictably, pointed out the observation matches expectations from artificial nickel production. Not that the comet is a factory, but that if it were a technological object with nickel-based components, or a nickel-rich surface coating accumulated during travel, solar heating could ablate that material. The lack of iron would simply reflect the eroded material's composition. The counter-argument is straightforward: why would an advanced civilization use easily ablating materials? If designing an interstellar probe to last billions of years, you don't use materials vaporizing near a star. Unless vaporization is intentional. Unless releasing a material plume serves a purpose. Cooling, mass shedding for trajectory adjustment, or signal generation creating a visible marker. Or, unless the accumulated coating wasn't part of the original design. Interstellar space isn't empty. At 60 kilometers per second, even diffuse gas/dust impacts with significant energy over millions of years. A spacecraft would accumulate surface material, just like a comet. If that material was rich in certain elements. Based on traversed galactic regions, you might see unusual compositions. The VLT data doesn't prove any of this. It simply establishes 3I Atlas is behaving anomalously. Nickel without iron, extreme production rates, emission timing, none fit comfortably into comet models. And nickel is just one piece. Comet tails point away from the sun. This is Come Try 101. Not because they follow the comet's motion, but because they're pushed by solar radiation and the solar wind. Photons carry momentum. Billions per second striking dust/gas transfer that momentum outward, creating the characteristic tail always streaming away from our star. Direction is so fundamental that astronomers spotting a comet can immediately tell where the sun is. On July 21, the Hubble Space Telescope captured the highest resolution image yet of 3I Atlas. The comet was 277 million miles from Earth, still inbound toward its October perihelion. The image shows a diffuse glow ahead of the object, pointing toward the sun. The glow is elongated, 10 times longer than wide, forming a teardrop/jet-like structure. In the direction where a tail should stream, there's nothing. No bright plume, no extended dust trail. Just faint scattered light fading into background darkness. The glow is an antitail. Antitails aren't completely unknown. Sometimes, under specific geometry when Earth passes through a comet's orbital plane, we see dust left behind in the orbit stretching in front of the comet, a perspective illusion. But 3I Atlas isn't in this configuration. The viewing angle doesn't support a perspective effect. The forward glow's brightness profile doesn't match orbital dust expectations. David Jewett, UCLA, leading Hubble observations, analyzed surface brightness versus distance from the nucleus. In a normal coma, brightness falls off gradually, dust spreads, dilutes, intensity drops following a gentle power law. 3I Atlas's forward glow drops with a projected power law slope of -3. Corresponding to a 3D emissivity profile with a radial slope of -4. This is much steeper than typical solar system comets. A steep fall-off suggests the glow-creating material is concentrated near the source and dissipates rapidly. Either the material is extremely fine-grained and quickly pushed away by radiation pressure, or there's active jetting from a specific nucleus location creating a directed plume. Jewett's team interpreted this as dust evaporating from the sunward side. Solar heating is strongest there, ice sublimates, dust lifts, the dust cloud expands forward before radiation pressure pushes it back. A reasonable interpretation, but it requires the comet shedding material asymmetrically, with the sunward side dramatically more active, unusual, but not impossible. Harder to explain is the absence of a dust tail. If dust is lifting in sufficient quantities to create the visible forward glow, that dust should persist. Radiation pressure pushes it outward, the comet's motion draws it into a tail. We should see something. Unless dust particles are extremely small interacting so strongly with light, they're blown away almost immediately, creating a faint haze, not a distinct tail. But such small particles are also quickly destroyed by solar radiation, breaking down until essentially invisible. Or, unless most of what we're seeing isn't dust at all, but gas. Gas doesn't form persistent tails like dust, it disperses, thins, becomes transparent far from the nucleus. But if it's primarily gas creating the forward glow, we're back to composition questions. What gas, at what rate, and why so directional? Another possibility explored by Loeb and colleague Eric Quito. If 3I Atlas is generating its own light, not just reflecting sunlight, the brightness profile would differ. Internal energy sources create emission falling off steeply with distance simply by moving away from the source. This isn't wild. Some comets show faint airglow from molecules excited by solar UV. But those emissions are well characterized. We know expected wavelengths, intensities, structures. The Hubble image is broadband, capturing a light range. Without spectroscopy of that specific forward glow, we can't determine if it's purely reflected sunlight or includes an emission component. We can say the structure is anomalous, forward-directed, steep falloff, no corresponding tail. These features together create a picture that doesn't fit standard comet models without invoking special circumstances. Importantly, this jet/plume's orientation points in the direction of motion. The comet travels sunward, and the glow extends ahead in that same direction. If you wanted to design a braking system for an interstellar object, releasing material forward creates thrust in the opposite direction. It's inefficient compared to rocket propulsion, but over long timescales with continuous mass loss, it could produce measurable deceleration. 3I Atlas has shown no measurable non-gravitational acceleration. Multiple teams analyzing its trajectory found motion consistent with gravity alone. But that analysis has limits. Small accelerations get lost in noise, and the observation window is short. If it were decelerating slowly, adjusting trajectory via directed mass loss, we might not detect it yet. The forward jet might be entirely natural, ice sublimating from a rapidly spinning, irregular nucleus. The image alone can't tell. But combined with other anomalies, nickel emissions, chemical composition, trajectory, it adds to a pattern where each observation can be explained naturally. But the collective picture becomes increasingly strained. You can have a comet with unusual chemistry, an odd trajectory, or asymmetric outgassing. But having all these in a single object, the third interstellar visitor ever detected, starts pushing against statistical expectations.